The theme of today is backtracking. But before we get started, there are two preliminary things which we learn in our first year of college. If you have studied C programming or whatever, you must have heard about these concepts called as pass by value and pass by reference. How many of you have heard about it? If yes, then can you tell me what are these? What is pass by value and what is pass by reference? Very simple, right? So let's say there is a function func which takes an integer x, right? It's a void function, all right? It's a void function. Now you are calling this from your main. So inside your main, you had a variable x, which was equal to 5. And now you call func of 5. Sorry, not func of 5, func of x. X is equals to 5, and you call func of x. Now here, if you do x plus plus, if you do x plus plus, will this change be reflected inside this x? Will it be reflected? The answer is no. Why? Because you are passing it by value. So when you pass it by value, a new copy of it gets created. So imagine this is your computer memory. In your computer memory, there is an x. This x is of main, whose value is 5. Now when you invoke func and pass x, then a copy of x is created. That copy is exactly equal to 5, but that copy belongs to func. So if you do x plus plus, it is this particular x which gets changed. This x is changed, that x is unchanged. Now, a lot of times we desire that the changes made here should be reflected in the calling function, right? So in that case, you choose to pass by reference. So there are different ways you use pointers, references, and all that. In languages like C++, you can just put this thing, ampersand mark, and it would be simply pass by reference. So, okay, it was just a quick refresher. Now let's get started, and let's get started with a very well-known question. It's probably maybe asked thousands, would also be less, maybe lakhs of times in interviews. So, have you guys heard of something called as permutations? What is permutation? Permutation is nothing but orderings, different orderings of an item. So let's say, for example, you have 1, 2, and 3. Now, how many different permutations can it have? So we can say that the thing with permutation is that any permutation that you make, it should contain all these items. So all the 3 items should be there. You cannot miss any of those, right? The only thing is you can change their order. You can shuffle them. So you can have something like 2, 1, 3. This is a permutation. 2, 3, 1 is another permutation. 3, 2, 1 is another permutation. In fact, 1, 2, 3 is also a permutation of itself. There are so many permutations, right? But if you have to list them down, how would you go about it? So this is the problem which we'll be solving, that how do we list down all the permutations? Okay, before doing that, can you tell me the count of permutations? What will be the count of permutations? So here you are saying 6. So how does that answer come? I can say that every permutation will be of size 3, right? Now, initially I have got n elements, right? So the number of elements I can choose for this position is n. Any of these 3 can be picked and brought over here. Now, when I have picked one item from here, the number of items that are left are n minus 1. So the number of choices for this position is n minus 1. Now that I have chosen 2 items from this list, the number of items remaining is n minus 2. So the number of choices here is n minus 2. So on and on, for the last position, there will be only one choice. Now, if you have learned about some basic permutation and combination, you can use rule of product and you can say total number of choices will be product of these values, which is 1 n into n minus 1 into n minus 2 all the way till 1, which is n factorial. In this case, n is 3 and 3 factorial is 6. So yeah, there are 6 different permutations of 1, 2, 3, and you can list them down: 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and then you have 3, 1, 2, and 3, 2, 1. So these are the 6 different permutations. But how to list them down? What can be the way to go? Any thoughts? N factorial only if the elements are not repeated. That's a very good thought. Yeah. For now, what we'll do is we'll assume that there are unique elements to keep things simple. And then we will consider the case that also contains repeated elements. But yeah, so what can be the way forward? So let us understand it. So guys, what we can say is that, hey, we want to create a permutation. Every permutation will be of size 3, right? Now, what I told you over here was that, hey, for your first place, there are n elements to choose from. And what are those n elements? This, or that, correct? So let us do exactly that thing without making any amendment. Let's do exactly that thing. So I would say that, hey, let's start with deciding that what element can come here. Then you can immediately realize that there are three choices, three different choices. So here I can either place a 1, or I could have placed a 2, or I could place a 3, correct? And now go on doing the same thing for other subsequent positions also. So now if you're wondering that how many different elements can come here, if I ask you this question, what will you tell me? What all elements can I place here? Given that I have already used 1, I can either place 2 over here, or I can place this 3 over here. So there are two choices. Because there are two choices, let us exercise those choices. So you can either place a 2, or you can place a 3. And then go on. Now finally, here, how many choices do you have here at this position? Given that you have taken 1 and 2 already, only 3 is remaining. So you can only place 3 over here, right? And you can go ahead and do that. And thereby you will get 1, 2, 3, which is your first permutation, right? And now the same idea can be repeated here. How many choices do you have for this position? You will say that I have already used 1, 3, only 2 is remaining, so I can only place 2 over here. And if you do that, you will end up getting 1, 3, 2. So this is your second permutation. And now you can do the same thing everywhere. Like you can do the same thing over here also. You can say that I have used 2. So for this position, I can either have a 1 or I can have a 3. If you put a 1, you'll get this. If you put a 3, you'll get this. And now with the same logic, for this position, there is only one choice. I have to put 3 over here. And here I have to put a 1. Correct? Same logic here. For this position, I can either put a 1 or I could have put a 2. And now again, at this position, I have to put a 2. And at this position, I have to put a 1. So can you see all the 6 permutations have been listed? Can you note it? Right? All right. Now, in fact, I can say that, hey, total number of permutations at this level is exactly equal to n factorial. And you can see it through this decision tree also. How? Can you tell me how many arrows will be there at the first level? The number of arrows is dependent upon the number of choices that you have for first element. How many choices do you have for first element? N choices. So, because you have n choices, there will be n different nodes over here. Now, for this second position, how many choices will you have? N minus 1. So you will have n minus 1 choices here, n minus 1 choices here, n minus 1 choices here. So each of these n nodes will have n minus 1, n minus 1, n minus 1 choices. So the number of nodes here will be n into n minus 1. And with the same logic, here it will be n into n minus 1 into n minus 2. And at the bottom, it will be n factorial. So this way also I can say that the number of permutations that I would end up generating in this process will be all n factorial permutations. Is that clear? How many of you understand this idea? Yeah. All right, awesome. So now we just want to replicate this idea and generate all the permutations quickly. Okay. So how can we go about it? Let's say you have got a simple array which contains 1, 2, and 3, right? You have got 1, 2, and 3. Now, I know for sure that let's take this array like that. And I can think and say that, hey, at this position, I can either have a 1, or I can bring 2, or I can bring 3, right? So basically, there are three possibilities, three different choices coming out from here, right? Now, how do you bring an element over here? Let's say if you want to bring 3, how do you bring it? Swap. The simple idea is swap. So you can swap this element with that element, and that way this 3 will end up coming over here, right? So now if you do that, if you go ahead and do that, you would say that, hey, the first choice is that just swap this element with itself. So swap this 1 with 1, right? And the second choice is you swap this 1 with 2. And the third choice would be you swap this 1 with 3. If you swap this 1 with 1, it'll continue to be like that, right? And now you reach to the next element. Now you want to decide how many elements, how many different elements can be placed here. Now, when you want to decide how many different elements can be placed here, those choices are just from here to here because this element is fixed, right? You decided to fix 1 over here. And now if you have to figure out how many different elements can be placed here, then it would either be 2 or it would be a 3. So going by that logic, you can either swap 2 with 2 or you can swap 2 with 3. If you swap 2 with 2, it will go like that. And if you swap 2 with 3, we'll see what will happen in that case. Now here finally, you just have 3. So when you have just one element, you can just stop. This can be treated as your base case. When you just have one element, just stop. Because because there are no further choices. There is only one choice, so let it stay like that. Now the control goes back to the parent function, and now you execute this thing. When you execute this thing, you swap 2 and 3. When you swap 2 and 3, what happens? It becomes 1, 3, 2. So it becomes 1, 3, 2. And this is your second permutation. Now the control goes back to the parent, and then the control goes back to its parent. And now you execute this thing, right? And here, what you wanted to do was you wanted to swap this and that. Now keep it in your mind that if you are passing this array by reference, you're not creating a new copy. If you're passing it by reference, then it would definitely have got changed to this because you performed a swap. So that swap would be reflected over here. So now the true picture of this would not be 1, 2, 3. It would be 1, 3, 2. Now let's think about it. What's problem with it? So if you go ahead and keep on following this approach, you would say, hey, let's swap this and that. Then you will get 3 over here, and then 1 over here, and then 2 over here. And now you would say, now here there are two choices, either swap 1 with 1 or swap 1 with 2. So if you swap 1 with 1, you will get 3, 1, 2, and this is your base case. And then when you execute this thing, you swap 1 with 2, you get 3, 2, 1, right? And now when the control comes back to this and goes back to that, the array has changed to 3 to 1. So now your new array is actually 3 to 1. Now, when you are executing this particular thing where you wanted to swap this and this, so you would end up swapping this and that. The moment you do that, you will end up getting 1, 2, 3. Now I can tell you for sure that with 1, 2, 3, you will never be able to generate a permutation which is starting with 2. So see, you have generated permutations like 1, 2, 3, 1, 3, 2, which are starting with 1. And you have generated permutations like 3, 1, 2 and 3, 2, 1, which are starting with 3. In this case, when you perform swaps for this element, you will see, because you have fixed your first element to be 1, right? So you will never be able to generate a permutation of the form 2, 1, 3 and 2, 3, 1. These will get missed. And why it happened is because what you desired for is not happening. Your desire was that when the control comes back to this function, my array should be as it was. So if it was 1, 2, 3, then after this function call is over, it should continue to remain 1, 2, 3. Then only if I swap this and that, I will get 2, 1, 3 over here. And now when the control comes back to this, it should remain 1, 2, 3. Because then only if I swap this and that, I will get 3, 2, 1. Right? So this is one problem with passing this thing by reference. If you pass this thing by reference, you will end up getting the wrong output. So what are you actually doing over here in this entire logic? The logic is very simple. The logic just says that if you have an array containing 1, 2, 3, 4, 5, 6, let's say, and you are at index 0. When you are at index 0, you realize that you can either swap 0 with 0, or you can swap 0 with 1, or you can swap 0 with 2, or you can swap 0 with 3. So the number of choices that you have are 1, 2, 3, 4, 5, 6. When you swap 1 with 1, you get 1 over here, and then you're deciding for others. If you swap 1 with 2, you get 2, and then in this case 3, 4, 5, 6. And then you move on to the next index. So now your index becomes 1. It becomes 1 everywhere. And now you repeat the same thing at the next index. So whatever is the value at next index, you try swapping it with itself or the element after it or the element after it or the... So you make so many calls. You make n minus 1 different calls at this level, right? So I can simply imagine that there is a function where I am passing some current index and I am also passing my array, right? And then what I end up doing is I end up swapping my index with j. And what is this j? This j is from index till n minus 1. That was the idea, right? Because I told you, when you come at position 1, then you want to swap this element with this element or this element with what is there after it or further after it or further after it and so on and on. That's the idea. That's how you code. Now, in this case, like we have seen, even if we implement this approach, we are going to get wrong answers because if our array is being passed by reference, the array will be modified and that would lead to issues, right? Now, what is the solution to it? So before talking about the solution to it, I like to show you some code so that you kind of really believe what's the problem with it. This is a question where you are asked to generate all the permutations. All right. Now, I have made certain changes over here, certain simple changes over here. But if I do what I told you to do, let's say pass this array by reference and pass the index I right after it. Okay. And now this is my base case where if my index touches the last element, then I simply push that permutation into our answer vector and then we return. And now this is our normal case where I iterate from index I till n minus 1. And what I do is I swap nums of I with nums of j. If I do this thing and if I run my code, you will end up seeing that I'm getting wrong answers. You can see that 1, 2, 3 has got printed 2 times. So I told you, right? I told you that no permutation starting with 2 will be printed. So I had to print these 2 permutations, but I could not print that. And why it happened? Because I'm passing it by reference, and because of that, the things are changing. So yeah, see, all of you are suggesting to undo, to backtrack. So yeah, backtracking is definitely the best way to deal with this situation. But if you do not know backtracking, what would you do? You would say that, hey, let's pass by value. Instead of passing by reference, let's pass by value. Now, if you're passing by value, in that case, you will have to make sure of one thing. And what is that one thing? You would say that, okay, first remove this thing from here and now come here. And now, because you want to pass by value, how you want to pass by value is you want to create a new array. And in that new array, you want to swap index I and index j, and then you want to pass that new array. So how I can go about doing it is, I would say, let me create a copy of the nums. And now I intend to pass this thing to the next function call. So I'll make swap inside this. And after making swap inside this is exactly what I'll pass. Now, if I run this code, it gives me accepted. And if I submit it, it gets submitted. So do you understand why it worked? It worked because in this case, you are not disturbing the input that a function call has. So let's say your initial function call has 1, 2, 3. That 1, 2, 3 will remain 1, 2, 3 because you are not disturbing it. You are creating a copy of it and you are disturbing that copy and passing that copy. Now that other function which you call, that also does the same thing. It keeps it input with itself and it creates a copy, disturbs that copy and passes that copy to the child. And it gets accepted because here the test cases are not that heavy and all, and anyways the value of n is very small. But do you understand it? Do you understand the difference between the previous approach and this approach? How many of you get that? Okay, all right. Now, what is something which is bad about this approach? The bad thing about this approach is that in every function call, you will be creating a new copy of the vector. You will be creating a new copy of the vector, and when you create a new copy, you will be using extra space and also extra time, right? So here, exactly here, backtracking comes into picture. If we pass nums in place of current, then uh, if we pass nums in place of current, then it also pass by value. Yeah, but you would not want to do that. You would not want to directly swap nums, and why you would not want to swap nums, I'm telling you. Just imagine. Uh, because when you are at index 0, you want to first, let's say you are swapping 0 index and 2 index, right? And if you go on to the next iteration where you want to swap 0 index and 3 index, you don't want that effect to be reflected in that. Because when you swap 0 and 2, second element comes here and for 0th element goes there. Now, if you intend to swap 0th element with third element, it will not be the real 0 element. So what you are actually doing here, what I am doing here is that if I am disturbing the array, before disturbing it, I am creating a copy and disturbing that copy instead of disturbing the actual input array. So before you learn about backtracking, it is immensely important to understand that why backtracking? Why? If we can solve all the problems by passing things by value, you can pass all the input by value, no backtracking is needed. But it has a major drawback. And what is that major drawback? Time limit, memory limit, because you are creating a new copy each time. If ever you see any backtracking algorithm or if you have to code a backtracking logic, you will kind of appreciate it. But why at all? Okay, so the idea of backtracking is pretty simple. Do, recurse, and undo. So whatever changes you have made, you are supposed to undo that change when your job is done. That's it. For example, if you had an array which contained 1, 2, 3. Let's say you made a function call where you swapped 1 and 2. So it became 2 and 3. And then it did its job, made further function calls, whatever. When this function call returns back, you should undo your action. And what is the undo of swap? Let's say you swapped index I with index j. Undo simply means you swap them back. Because if you have swapped this and this, how you can undo this action? By swapping them once again, by swapping them back once again. That's the simple idea, right? Just think of it in this manner. You have an array which contains 1, 2, 3, 4. Now you're performing a sequence of operations. You are swapping index 0 with index 2. So if you do that, swap this and that, you will get 3, 2, 1, 4. And then you are swapping index 2 with index 3. And that way you are getting 3, 2, 4, 1. And then you are swapping index 3 with index 0. And that way you are getting 1, 2, 4, 3. Now, so these are the operations that you have performed. Operation 1, operation 2, operation 3. This was your initial array and this is your final array. If you want to backtrack your way to the original array, you will have to undo these operations. But in what order would you want to undo these operations? Would you first want to undo this and this and that? Or would you want to undo them in reverse order? You have to undo them in reverse order. You have to first undo this operation. Let us just undo it. Undoing this operation means swapping 3 and 0 again. So if you swap index 3 and index 0 again, you will end up getting 3, 4, sorry, 3, 2, 4, 1. Now, similarly, you will have to undo this step. So if you swap index 2 and index 3, you will get 3214. And similarly, if you swap index 0 and index 2, you will get 1234. So that's a very important idea. Now, if you look at any recursive function call, let's say there is a function that calls another function, that calls another function, that calls another function. And let's say it performed operation 1, operation 2, operation 3. Now the return happens from bottom to top. So naturally the first undo happens to operation 3 and then operation 2 and then operation 1. And I'll show that to you through a very, very simple example. So let's demo it now. Let's say you have 1, 2, 3. You are at index 0. So we all know that at index 0, the first option is you swap 0 with 0. The second option is you swap 0 with 1. And the third option is you swap 0 with 2. But we all know whenever the control comes back, we would want to swap 0, 0 again. So we are not doing it again because if you do it again, it doesn't make sense. So when this function call is over, you would swap them back again. So right now you have swapped 0 and 0. So it continues to be 1, 2, 3, and you move on to the next index, which is index 1. Now at index 1, there are two operations. You either swap 1 with 1 or you swap 1 with 2. If you swap 1 with 1, you are going to get 1, 2, 3, right? And in that case, you will move on to the next index 2. So whenever you move to index, which is final index, you can just stop. You can return from there. And now we all know that whenever control comes back here, we undo our action. So we will swap back 1, 1 again. So when you swap back 1, 1 again, it will be back to the same thing. It doesn't really make a lot of difference. This thing is interesting. Here, if you swap 1 and 2, if you swap 1 and 2, what's going to happen is you're going to get 1, 3, 2. And you will move on to the next index, which is index number 2, right? Now, when you backtrack, you know you will undo your action. And undoing your action means swapping 1, 2 again. So when you swap 1, 2 again, this 1, 3, 2 will be back to 1, 2, 3. And now when you backtrack again, you will undo your action, which is you swap 0, 0. When you swap 0, 0, this 1, 2, 3 will be back to 1, 2, 3. So this is how it kind of works. Like if you look at the flow, you went like this. Your first action was swap of 0, 0. Second action was swap of 1, 1. But when the control traversed back, you swapped 1, 2, and then you swapped 0, 0, and then you got back to your original state. So you will consistently see in this backtracking exercises that whenever the control comes back to a function, the input is restored to its original form. And that is the entire idea of backtracking, right? In order to solve an issue with space consumption, aren't we increasing the processing time? No, not really. Where is it? You were swapping earlier also, and you are swapping here also. So two swap operations are not much of a big deal, right? If you're just swapping two integers, it's not going to cost you a lot. It's order 1, right? Okay, now when you swap 0 and 1, what's going to happen? You will get 2, 1, 3. You will move on to the next index, which is index 1. At index 1 again, you have two choices. Either you swap 1 with 1 or you swap 1 with 2. When you swap 1 with 1, it will continue to be 2, 1, 3. You go on to the next index, and this is your base case, you know. Now, when you backtrack, you undo, which is you swap 1, 1 again. So if you swap 1, 1 again, it will be back to 2, 1, 3 only. Now this is interesting part where you swap 1 and 2. When you swap 1 and 2, this thing now becomes 2, 3, 1, and you reach index 2, which is your base case. Now, if you look at the flow, first you swap 0, 1, then you swap 1, 2. The first function to exit will be this. So you will now undo 1, 2. When you undo 1, 2, you will swap this and that, and you will come back to this. Now, when this function returns, you will undo this action. So you will swap 0 and 1, and you will be back to 1, 2, 3. So this is how it works. This is how it entirely works. That you go from your parent to child to child to child to child, and you perform a sequence of operations. And when you come back, you simply undo your mistakes. You undo your, not mistakes, you undo your operations. And that way you get the input back to its original form, to its original state. Is it making sense? How many of you understand the essence of backtracking through this example? There is very, very simple essence of backtracking. You do an action. That action could be anything. And then you recurse, you make function calls. When that function call is over, you undo your action. So if the action that you did was adding 5, what will be the undo of it? -5. If you divide it by 100, what will be undo of it? Multiply by 100. If you inserted an element, let's say your data structure was a list, and you inserted an element, what will be the undo of it? Delete that element. Exactly. This is common sense. Figuring out do and undo, this is common sense. Okay. So now if you have to code this stuff, what is the change that you really need to make? There is a very, very tiny change that you really need to make. So I'll take you guys back to the coding screen and share my screen and show the code there. So see, there is not much. In fact, there is nothing that we need to do a lot. We'll just say that, hey, this time, let's pass this thing by reference, and we are not passing by value now. So remove this comment, remove this thing. This is no longer needed. And you swap nums of I with nums of j. So this is your do. This is your do. All right. This is your recurse. All right. And finally, you have to undo whatever you have done. So undoing whatever you have done means you will swap nums of j with nums of I, and this step is your undo step. Does that make sense? Do you get the code? Yeah. So that's really all about it. Now what we'll do is, in interviews, what happens? When you give a solution, the reward for that is harder question. If you give solution to an easy question, the interviewer moves on to a harder question. That's what happens, isn't it? So now let us complicate this question just a little bit. So now somebody asks you that, hey, tell me one thing. 1, 2, 3 is our input. Print all the permutations in lexicographic way. You understand lexicographic way? Lexicographic means that the permutation which is lexicographically smallest, that should be printed first. So which is the lexicographically smallest permutation of this? Where it is sorted in ascending, 1, 2, 3. And which is the lexicographically largest permutation? 3, 2, 1. In between this and that, everything else comes. Can you tell me which is lexicographically greater? 3, 1, 2 or 3, 2, 1? Out of this and that, it is 3, 2, 1, right? You understand? How do you compare? 3 and 3 are matching. 1 and 2 are not matching. So whenever there is a mismatch, you check which value is smaller, which value is greater. Of course, 3, 2, 1 would come later in the dictionary compared to 3, 1, 2. It's basically lexicographic order is dictionary order, nothing else. So quickly tell me one thing without taking a lot of time. Is this algorithm taking care of lexicographic ordering? Let me just write down what it has printed so far. It has printed 1, 2, 3, and then it printed 1, 3, 2, and then it printed 2, 1, 3, and then it printed 2, 3, 1. What should be the next two values that it should be printing? If we are interested in lexicographic order, 3, 1, 2 and 3, 2, 1. Okay, so far till here, has it done a good job? Till here, I think yes, because it first printed 1, 2, 3, and then 1, 3, 2, and then 2, 1, 3, and 2, 3, 1. So till here, it has done a decent job. Can you expect the same thing here also? Let us do that. If you swap this with that, you will get 3, 2, 1. All right. Now you are at index 1. And now what do? You swap index 1 with 1. That way you get 3, 2, 1. And then in this call, you swap this with that. So you get 3, 1, 2. So here it freaked, because instead of printing 3, 2, 1 after 3, 1, 2, it did the reverse. So it means that our current algorithm is not printing in lexicographic order, right? And now let us root cause this. Let's find the root cause of why it is not printing in lexicographic order. So what do you guys think about it? What could be the reason of it not printing in lexicographic order? If you take a look, what has happened here is, like, when you swapped 1 with 1, the remaining array was 2, 3, which is sorted. Okay. When you swapped 1 with 2, the remaining array was 1, 3, which was also sorted. But when you swapped 1 with 3, 3 came here, the remaining array was 2, 1, and it was not sorted. So whenever it so happens that the remaining part is unsorted, things go and crash. So what we really want is that at every point, the remaining section or the remaining set of elements must be sorted. At every point, the remaining section of elements should be sorted. This is what we wish. Now, this will not be achieved in the current approach, because in the current approach, if let's say you have 1, 2, 3, 4, 5, and you are making all the 5 function calls. Let's say one function call that you made was this, and in this function call, you performed a swap of this and that. The moment you do that, you get 4, 2, 3, 1, 5. Is the remaining section sorted? No, the remaining section is not sorted. So we have to come up with an approach where the remaining section is always sorted. Only then we will be able to, generate the lexicographic permutations. So what to do? What to do about it? If you are just blindly swapping, then the remaining part becomes unsorted. So what to do? Sort it. That's a very good idea. That's a very good idea. But the problem with this approach is, okay, you think what will be the problem with this approach? Just think about it. When you swapped, the undo operation was very simple. It was just an unswap, right? But when you sort, let's say you sort it and you got this thing and you're very happy about it. There is a big problem. How will you unsort it? And unsorting means getting it back to its initial form, right? And that is going to be a little nasty with respect to implementation. So you'll have to remember that, yeah, this was the initial form and now I sorted it. So you'll store this initial form somewhere, and when the control comes back, you will get it back to its initial form. Doesn't look like a great approach. I mean, it definitely would be a correct approach, but definitely not a great approach. Is that making sense? Do you get it? So the idea to sort is not so clean and clear, right? Now here, what you can do is, let me ask you, this question is in different style. So all that you want is, if you have 1, 2, 3, 4, 5, and let's say you're deciding how many elements can come here. So there are 5 different possibilities. Let's say if you're talking about this possibility, in this possibility, you want to swap 1 with 4. This is what you want. Is there a way you can get 4 over here? Because see, at the end of the day, you want to get 4 over here. This is the most important thing. Is there a way I can get 4 over here and also ensure that other elements are completely sorted? Yes. So left shift, or you can say left rotate. So what I would end up doing is, I would bring this element on over here. I would push this element here, this element here, and this element here. This is what I would do. The moment I do that, you will have 4, and you will have 1, 2, 3, 5, and it is naturally sorted. It's naturally sorted. Now let's say you come to this index and you realize there are 4 operations that you can do, which is you swap this with this, or you swap this with this, or you swap this with this. Let's say you want to swap 1 and 3. So I would say, instead of swapping 1 with 3, Why don't you do a left rotate, which is you bring this element on here and this there and this there. The moment you do that, what will happen? You'll get 4, 3, 1, 2, 5. The remaining part is again sorted. So instead of swapping ith element with jth element, I would say perform a left rotate from index I to j. Is it making sense? How many of you are able to absorb this concept? And now tell me what will be the undo of this? What will be the undo of left rotate? Very simple, right rotate. Excellent. Right rotate. That's it. Job done. So can you write a function to perform left rotation? It is very easy. I mean, you learn how to do it in your first year of engineering, right? All that you have to do is you just have to copy at index I the value which was at I minus 1. Then here you copy. So this is how you kind of basically left rotate, and the opposite of it would be to right rotate. Okay, so like you can just write a separate function which performs left rotation and separate function which performs a right rotation. And then you can just use those and you will see that then the way in which the output will be generated, it will be completely sorted lexicographically. So see, what can you see here? There is a function to left rotate the array from I to j. Very, very simple function. It copied the jth element in a temp, and then it is pushing just k minus 1th element at index k. That is how you one by one right rotate. Sorry, left rotate. Okay, so this is the code for left rotate, and the code for right rotate is also pretty similar. Here you push k plus 1 at k. It's just like if you call this clockwise, then this is anti-clockwise. That's it, nothing else. And now the only thing that has changed is that instead of swap, I'm doing left rotate and right rotate. And if I kind of run this code, let's say you run this code, you will see that your outputs will end up coming in lexicographic order. Like you can see first you got 312 and then you got 321. Okay. But if I change it to simple swap of ij followed by swap of ij. And then if I run this piece of code, I mean, it's obvious. You will end up seeing, okay, why did we get a wrong answer here? It's probably because sub I with j, ji. Okay, now we are no longer using these methods. Line 29, what is wrong with line 29? No, whether you swap ij or ji, that's all right, right? And I think I'm really making some silly mistake somewhere. All right. Okay. Answer nums and index I is equals to this j swapping index. Sorry. Oh, that was really silly. Nums of I with nums of j. Correct. We are swapping nums of I with nums of j. The swap method is not defined. I'm using the inbuilt swap method that exists. All right. So now if you run this code, I just wanted to show you that this will produce the right output, but that right output will not be sorted. Here 321 would end up appearing before 312. That's the idea. Did you get it? Now, there is one question, which is again, like, let's say you have solved this question and interviewer is still not satisfied. Interviewer would just bombard another question at you. So you can think about this question. It's another good variation of it, where it is said that now, see, so far you had distinct elements. But what if you have repeated elements? Let's say you have 1 to 1. Can you tell me how many permutations will it have? So the first one is 1 to 1. The second one is 2 1 1. And then what else? 1, 1, 2. Do I have anything else? No, there are no other permutations. So here I want you to understand that if elements are repeated, then you do not have n factorial permutations. Number of permutations is smaller. Now, if you use the same approach that we just discussed here to generate all the permutations, if you use this approach, will you be able to print all the distinct permutations? Will you be able to do that? No, you will not be able to do that. So what to do in that case? So I've seen 90% of people, when asked this question in interviews, they say that, hey, let me use the same approach, but let me store all these permutations inside a set. So let me keep a set of vector. And tell me how many of you got this exact same approach in your head? That what you will do is you will store all of them in a set, and set will automatically take care of discarding the duplicates, right? This approach will not be appreciated. Because when you are using this approach, you are relying completely on the internal implementation of set. You have done nothing from your side to show that how you yourself can filter the duplicates out. So this solution will not be accepted, because when you use a set, it adds to additional space, additional time, everything. And on top of that, it is not showing the interviewer what he wants to see, what he wants to see. Anybody and everybody can use set, right? Even if you probably ask this question from ChatGPT, and if you ask it to probably come with a very brute force solution, naive solution, it would say, if you tell ChatGPT, hey, suggest me a way to do this thing, okay, yeah, ChatGPT would give you the right solution right away. I mean, it would tell you that, okay, use, because it's a very famous problem. It will not probably ask you to think about set. So it will not probably make you think from the first principle. But if you think like a human from the first principle, you would think, let's use a set. But I told you, using a set is not the way out. So what to do in this case? How to think about it? So one of you is saying, do not swap with the same element again. Okay, that's a very good line of thought. Others also, just think about it. Okay, just think about it. And I have even made a video on this concept. So what I'll do is, on the Discord channel and on the community page, which is coming live in some days, I'll be putting the link to it. Watch it after you have given your 100%. Give your 100%. Think about how you will deal with this state, and then you can take a look at that.